the final project of signal and system, that is the analysis of a periodic signal and low pass filtering. That my team is from a group 1, and my name is Syakir Auza'i Ismail, and my matric number is CE240128, and my other member is Alexander Koay, that CE240071, and the other member is Hafizy bin Ismail, that his matric number is CE240073.
So the main goal of our project was to apply the fundamental theories of this course to a practical problem. We started with a periodic square wave, analyze it completely, and then design a filter to change its characteristic. Our objectives were fourfold. First is to model the square wave using the Fourier series. Second, to design a RC low pass filter based on our group's specific parameters. And then third is to validate all our theoretical results from our MATLAB script against practical simulation. And finally, to investigate how changing key parameters like the cutoff frequency and duty cycle affect the system. The specific parameters assigned to our group were a fundamental frequency of 100 kHz and a filter cutoff frequency of 650 kHz. So let's begin with the first task, is analyzing the input signal. So we use the Fourier series to build our square wave by adding sine wave together. On this slide, you can see how the signal become more accurate as we add more harmonics from 5 up to 20. The small ripples you see are an expected effect known as the Gibbs phenomenon. The bottom plot shows the signal's frequency spectrum. As expected, for a 50% duty cycle square wave, it has a DC component and energy spikes only at the odd multiple of our 100 kHz fundamental frequency. And next, we design our RC low pass filter. Our goal was to create a filter with a cutoff frequency of 650 kHz. The game plot on the left is the most important result here. It shows that the filter passes low frequencies at 0 dB and then start to block the higher frequencies. We can confirm our design is correct because the gain is exactly negative 3 dB, right at our target of 650 kHz. The plot on the right shows the phase shift introduced by the filter.
Thank you, Syakir. My name is Alexander, CE240071. Now let's look at the most important result of our project. What happens to the signal after it passes through the filter we designed? On this graph, the blue line is the input square wave we created, approximated with 20 harmonics. The red line is the final output signal that has been filtered. As you can see clearly, the filter has the rounded and sharp corners of the original square wave. Why does this happen? It's because the low pass filter has removed the high frequency harmonics. Those high frequencies are what created the sharp instantaneous edges of the square wave. By removing them, we are left with a much smoother signal. This result perfectly demonstrates the fundamental purpose of low-pass filter, and it shows that our theoretical analysis correctly predicts the output. We have built a RC low-pass filter using MATLAB software. So based on our cutoff frequency of 650 kHz, so now we insert our capacitor value of 2.4485 E negative 10, and also 1000 kHz for kilo ohms for our resistor. Then check our signal input of 2 pi 100 E3, which is 100 kHz. Then now run our simulation. For our simulation, our graph will likely almost the same as our theoretical coding waveform. Okay, now let's compare it. As you can see, the results are nearly identical. The shapes of the waveform, the rounded corners, and the amplitude are perfect match. This gives us a great confidence that our Fourier analysis and filter designs are correct, and it successfully validates our theoretical work. As you see the graph, it's nearly identical. Next, I will investigate the effect of a changing filter cutoff frequency. First, go to our transfer CN and change our denominator to, which is our 300 kHz, to 5.3052 E negative 7. Then apply it, enter. then run our simulation. Once it's done, click on our scope. Then here's our waveform. This makes the filter more aggressive for 300 kHz. As you can see, it removes more high frequency harmonics, and the output signal becomes much more rounded, closer to our pure sine wave graph. And next, for our 1000 kHz, which is 1 mega, change our denominator to 1.5915 negative 7, 1, then run our simulation. So for our 1000 kHz or 1 MHz, the filter is less aggressive, more harmonics are allowed to pass through, and the output signal looks much more sharper and moves more like a original square wave input.
For our final investigation, we explore how changing the signal duty cycle affect its properties. We analyzed 5 different cases from 10% up to 80%. On the left side of the slide, you can see the time domain graph. As you expect, the width of the pulse changes directly with the duty cycles. The more interesting result is on the right, is the frequency domain. Notice how the spectrum changes for the narrow pulse. Like the 10 duty cycle at the top, the energy is spread out very widely across the frequency. But for the wider pulse, like 80% duty cycle at the bottom, the energy become much more concentrated near the DC component. This is the key principle that changing a signal property in the time domain is predictable and significant on its frequency domain characteristic. In the conclusion, our team has successfully completed all the objectives for this project. We began by modeling a predict square wave using the Fourier series and analyze its properties in both the time and frequency domain. We then designed a low-pass filter for our specific cutoff frequency of 650 kHz and demonstrate how it reshapes our input signal. Crucially, we validated our theoretical result from the MATLAB script against the practical simulation and above a circuit simulator. In the Simulink, we found a very strong agreement between them. Finally, our investigation into varying the cutoff frequency, the duty cycle, confirmed the fundamental relationship between the signal parameter and its behavior. This project has been excellent practical application of the theory we have learned in the signal and system.